So I'm going to be talking to you a little bit today about parametric equations and how they relate to curves and cycloids. So this is sections 7.1.3 and 7.1.4 from calculus textbook. So parametric equations are very useful for representing curves. Now they're good for representing curves because many curves cannot be represented simply by a function in terms of x and y. Like this, like the graph for this function here, this oval, you can't really represent it as a simple x and y function. So you would want to represent it with parametric equations. So what that is, you're just taking a variable that is distinct from x and y, and you are using that variable to plot the points of x and y. And that variable is referred to as the parameter, and that's usually denoted as t. So it's a way of representing the x and y functions with another variable, an entirely separate variable. And so like as the parameter increases, the values of x and y start to trace out the path along the curve. So let's have a look-see at an example then. So let's say that we were asked to sketch the curve of the following parametric equations. X of t equals t squared minus 3, y of t equals 2t plus 1 on the interval from -2 to 3 for t. So this is pretty straightforward. What you'd have to do, all you have to do is you take as many values for t that you would want and plug them into each function and then plot the graph accordingly. For a pretty accurate representation, you'd probably want to do just the integer values from -2 to 3. Over here on this graph, they only did 3 points, and that gets you an idea of how the graph behaves, but you might not get the exact curve that it actually is. So the more points for t, obviously the more accurate your graph will turn out to be. So in this case, they just did t equals -2, 0, and 3. So they calculated that out. X of -2 equals -2 squared minus 3, which equals just 1. And then y of -2 equals 2 times -2 plus 1, which is -3. So that's just 1. The point is just 1 -3 at t equals -2, and that's where that is right there. X of 0, 0 squared minus 3, it's just -3. And 2 times 0 plus 1, that's just 1, so there's that point, -3, 1, and there it shows up right there. And finally, x of 3 just equals 3 squared, 9, minus 3, 6. And y of 3 is 2 times 3, 6, plus 1, 7. So the final point there is 6, 7. And that's where that shows up. They wanted to show you at what time or what t was at each point, which isn't a bad habit to get into with parametric equations. And I should also note that this was necessary to portray this graph here. You had to use parametric equations because this actually isn't a function. This doesn't pass the vertical line test. Therefore, you had to use parametric equations. So, with parametric equations, you might be asked to eliminate the parameter. So, this one's also pretty straightforward. All you're doing is pretty much just going backwards, right? So you're given parametric equations, and you're trying to simplify it or try to go back to having just a function in terms of x and y. So you're trying to go back to one function. So in general, you would just I wanted to do an example that's unique, but in general, you would just pick either the x function or the y function, and then solve that function in terms of t, or solve it for t. Solve it for t, and then whatever you get for t in terms of whatever you picked, you take that value and then plug it back into the other function for t. Then you just have the function in terms of x and y. But in this one's a little bit different. So we're asked to eliminate the parameter of the plane curve represented by the parametric equations of x of t equals 4 cosine t, y of t equals 3 sine t on the interval of 0 to pi. So we can rewrite those formulas as cosine of t equals x over 4, and sine of t equals y over 3. So you're just dividing each by their coefficients there. And to proceed, you must recall the trigonometric identity cosine squared plus sine squared equals 1. So we have a value for cosine squared, or for cosine and sine. So if we just take the squares of those, then the sum of those squares will equal 1. So that's all you have to do. You just x over 4 squared plus y over 3 squared equals x squared over 16 plus y squared over 9 equals 1. And you should recognize this as the form for an equation that's a circle. So it doesn't ask for you to graph it, but I just wanted to show it here. So that's what that graph looks like. And it's the complete circle because the parameter t is from 0 to 2 pi, which is an entire circle. Okay, so now we have cycloids and other parametric curves. So how a cycloid's been described to me was, imagine there's an ant, right? And this ant latches on to the side of a bicycle tire, and then the bicycle starts riding. A cycloid would be the path that the ant traveled along over time when he was attached to the wheel. So it is the path that you get from traveling along a rolling circle, or a rotating circle, in other words. That you can see this illustration of that. Like, here's where the ant would be, and then the tire moves and rotates, and there's the ant at time equals 1, or t equals 1, and then t equals 2. It keeps rolling and rolling, and then these curves here that you get from connecting those points are cycloids. So that's what that is. So here's the general parametric equations for a cycloid. It's x of t equals a times t minus sine t, and y of t equals a times 1 minus cosine of t. And a just refers to the radius of the circle, and t refers to the parameter, and that's usually just referring to time, just after a certain amount of time. So that's what a cycloid is. And then you also have hypocycloids. So definition of that is a curve traced along the circumference of a circle which is rolling on the interior of another circle. So we have to go back to the ant bicycle analogy. It's, instead of the bike traveling along a straight road, the bike is riding inside of a large wheel instead. So analogy sort of falls apart a bit, but it's just a circle that's rotating inside of a larger circle. Like this smaller one is rotating along this larger one, and this shape that is being formed by this red line here, that is the hypocycloid, using these two circles. So here are the general parametric equations for a hypocycloid. So you have x of t equals a minus b times sine t minus b times sine of a minus b over b times t. And y of t is, it's actually the same function. So a minus b over, yeah, you see that. So those equations look a little bit much, but if you know the variables, then it's really not too bad. Like, a just refers to the radius of the larger circle, and b is the radius of the smaller circle that is rotating. So once you know those values, you can just plug those in for the a minus b and a minus b over b, and then it looks better. So those are the general parametric equations for a hypocycloid using two circles. And finally, I want to mention cusps. So as you can see from this graph, there are like four pretty distinct sections of the hypocycloid. So that means that there would be four cusps for this hypocycloid. So cusps refer to hypocycloids. So they told me that a cusp, or the textbook told me that the cusp is a corner or pointed edge of the graph. So it's pretty much just any part where it looks like the curve is like changing directions. So, and the number of cusps is just the ratio of a over b. So the radius of the larger circle over the radius of the smaller circle. So like this is the one that we had. We had the larger circle had a radius of 4 and the smaller one a radius of 1, so it had the 4 cusps there. So what should be noted is that the uniqueness of the graph of a hypocycloid oftentimes comes down to this ratio. If you have an irrational ratio of a over b, then the number of cusps just get crazy. Like, look at this ratio when it's pi. Like, you can't draw that many cusps. It's just an absurd amount of cusps. And like square root of 2, it looks like it's maybe even more cusps, but they're like even more tightly packed together. So the really unique looking hypocycloids are the ones with ratio with irrational numbers. And also, even if you are still rational, just not a whole number, you'll start to get like a star formation going, which is also unique in its own way. So that's pretty much all there is to say about that. So that was parametric equations and how they relate to cycloids and other curves. Thank you.